Hi, my name is Matt Maxwell, and I'm a product manager for Tektronix Spectrum Analyzers. And this quick how-to video will talk about how to use RSA607A Real-Time Spectrum Analyzer controlled from a PC to conduct wireless LAN parametric RF testing for the physical layer test, testing against the IEEE 802.11 standards. So these kinds of tests are often done in both the R&D phases, design validation, and manufacturing test of wireless LAN modules, or maybe even semiconductor components to those modules. And then sometimes they may also be done in integration of the wireless LAN module to a larger device. The testing capability is important to understand that you can test against the wireless LAN standard or maybe your final end customer specification, and you need to have reasonable margin for your test to make sure you are measuring the device under test and not the performance of your instrument. So let's get started. The screen that we're looking at here is a spectrum display, but it's a real-time spectrum display where I have regular real-time controls, or I have regular spectrum analyzer controls like frequency, which can be changed, tuned to different frequencies. I have a reference level, which I can adjust to different levels. And I can also change, and there's the span, I can change the span. I can have narrower spans to narrow in. If I have a wider span, I have triggers activated right now. It's going to affect the triggers. And I can control the resolution bandwidth. And if I don't like the state it's in, I just backspace and hit enter again. What's interesting about this display is you've noticed it has a very good update rate with the max hold trace for what is really a very low duty cycle signal, which can be very helpful when you're trying to make sure that the signal is really present, to make sure the signal is really on, or the device is really on. So the way the software works is I have a button for selected displays. When I push that, I see a number of different displays that are available that I can choose from, which are organized into these different measurement folders. And down at the bottom, I have my wireless LAN analysis. I happen to have chosen some displays from above already for the real-time DPX display, the time overview showing the amplitude versus time, the wireless LAN constellation, and the wireless LAN power versus time. We don't see those yet because I need to reduce the size of the DPX display. So looking at these measurements, I've got wireless LAN power versus time, where it's measuring the burst power and the burst width in time. I see in the time overview, I've triggered on the signal, and I have a very long dead time before the next signal occurs. If I really want to know what that dead time is, I can increase the analysis length and wait till I see another one. But that's going to take longer and longer. Now I'm doing half a second, 500 milliseconds of signal before I see the next wireless LAN burst here. I don't even see it inside of that time. So I'm going to go back to a smaller burst, maybe 90 milliseconds. And then in this lower display in the lower left, I have the constellation diagram. So this is showing the 64 QAM version of the signal. And really what I want to kind of highlight here are the measurement parameters that are available for both controlling the analyzer from the bench as well as setting up parametric testing for that. So a helpful display here might be the wireless LAN summary. So I'll add that. And maybe now that we've seen the constellation diagram, it's just sort of a visual indicator. But if I pull up the wireless LAN test, I see the data's from warm-up period there, but I see the burst power index. I see the different EVM measurements for this 802.11G signal. And let's make this large here. I see the packet format, the data modulation, the guard interval, different components of the signals parameters for their error vector magnitude and average power. The SIG data, it's passed the parity check. Also up here in the start that I passed over initially, the IQ origin offset, the peak to average ratio, the frequency error from the expected channel 1, because I'm at channel 1 4.12 gigahertz, so I'm 4 kilohertz below that for this particular device, and that may or may not be within tolerance depending on the specs in the standard or your individual specifications. So the point here really is I have a very easy to drive piece of software that can perform these different analysis. The type of signal has been selected by 802.11g with a 20 megahertz bandwidth, which is the default settings. If I have more than one burst, I can select which burst that I need to analyze. There's the equalizer that's used, so it's training on the preamble and automatically detecting the type of modulation, in this case 64 QAM, that's being used, and it's pilot tracking based on the phase. We're not displaying any data at the moment, but I could choose to display just the symbols or the symbols and subcarriers. Looking at the analysis length, it's a 22,500 symbols. The EVM is in dB. I could look at the EVM in percent if I'd rather. And there's different preferences here, looking at the time units, the frequency units, and the radix, hex, or binary. There are, like I mentioned, a number of other wireless LAN displays available, like a spectrum emissions mask, channel power response, wireless LAN channel response, wireless LAN EVM, magnitude error, phase error, spectrum flatness, and symbol table are all available measurements within the wireless LAN capabilities. And with the SignalVu-PC software shown here, which controls the USB analyzer, I have support through 802.11ac signals. So pretty comprehensive set of measurements that can be used to characterize a wireless LAN module, either programmatically or performing troubleshooting for the module if something isn't working correctly. Looking, for example, at the constellation diagram shown here to find out if there's any issues, any problems going wrong there. And I see I've got good but not ideal points there on the constellation diagram. And I know that the EVM is now in percent. It's for everything 3.2%, 3.5%, something like that. So hopefully that gives you a little bit clearer understanding of the parametric testing available with the RSA607A Spectrum Analyzer and the SignalVu-PC software. I thank you for your time.
Find out more at Vicom's website.